What a chump. Okay. There's a chance we'll be meeting by Zoom on Friday.
Is there a chance I can have one more day on the closed last night?
Some stuff by.
Okay.
Does anybody else need more time on the web work that closed
There were
last
just
night?
two of them that were.
I know at least one. Okay, yeah, how about that? Let's do that.
Great.
You send me an email?
Yeah.
Just says web work time,
Yeah.
more.
Do that real fast.
Thank you. Which web work was it? Like 15? 15?
Right.
Yeah, I can check right now. 15, yeah.
Cool. Got it all wrapped out. Nice.
Concludes our ratio test one.
Yeah, beautiful. Nice. Good. Not a super tricky one, right? I mean, if we know where to look and what to pick apart here, this isn't too painful at all. Let's look at the absolute. Looks like I see a lot of folks waiting. So, alternating series, use the alternating series test. You need to identify the thing that's not alternating. So that's why I wrote this, and that's why I said that. And then I check these conditions. Is the non-alternating part itself always positive? Check. Does it converge to 0? Check. Is it decreasing? This one might be a little tricky, so let's address that. So I'm going to write out UN and UN plus 1. And why is this one strictly less than this one? Why is this the case?
It's a bigger denominator.
Thank you. That's all we have to say, right? Denominator got bigger. It's all positive. Here's another way you could see that. N plus 2 is less than N plus 3. That's pretty clear. When you take reciprocals, you flip the sign. So that's another way to see it. And you could also use that derivative thing that I talked about, where I said that f of n is 1 over n plus 2. So f prime of n would be negative 1 over n plus 2 quantity squared. That's always less than 0. No matter what n is, and n can't be negative 2 here, but that's okay. For big N, that's negative. That means we are moving down. So f is decreasing. Lots of ways to see it. There's 3 good ones. So this series converges by the AST. Cool. Then we go to conditional convergence. So we strip away the alternation and we answer the question, does this converge? What do we think? No. No, I'm seeing some notes. Yeah, somebody give me a good reason. I agree. It's basically the harmonic series, right? It's not the way we're used to seeing it. So let's actually address that. Because there's something really important and deep here. So this is the harmonic, the classic harmonic, right? And we start at 1, and it looks like this. And we know that that converges. This is basically the harmonic. It looks like I was starting at 1. So it's just missing a few things here. This turns into 1/3 plus 1/4 plus 1/5. The thing about series and convergence is it doesn't matter what happens in the first even million terms. It's long-term behavior that matters, and these two are basically the same up to infinity. So the same from here on out, and that means their convergence is the same from here on out. So that's a great way to do it. What tests could I use here to prove that? Like, let's say I didn't see that. What test could I use to show that that diverges? Comparison test, yeah. And I would probably use the limit comparison test. So by the LCT, we're going to compare with the harmonic series, the one that it looks like. So I create this limit, L equals limit of my given series divided by the general term of my comparator series. So I just take its reciprocal and multiply those together. You've seen this a bunch. And then what is that limit? 1. Beautiful. And that is not 0. So they act the same. So the series, since L is not 0, the series act the same in terms of convergence. So both diverge. Lots of ways to get at it. Sound good? We're gonna make things a little more interesting today as we head toward our final topic. So my goal, I hope to get this done by like Monday, and then Wednesday and Friday are just like working on stuff together days. That's my goal. Just got really a couple last things to talk about, but they're really important things to talk about. So I want to talk about power series, which takes everything we've been studying over the last 2 weeks and pulls it all together in a much bigger, more interesting problem. So given a series that looks like this, so I've got sum n equals 0 to infinity a sub n x minus x sub 0 to the nth power. Let's write out what that means, because there's a lot of symbols going on. So in other words, when n equals 0, I've just got a0 times 1. Plus a1 times x minus x sub 0 to the first, plus a2 times x minus x sub 0 squared, and now we get the rhythm of what's going on there. This is like an infinite polynomial, right? I see powers of x. I've got a variable in here, so this is what's new. So x is a variable, and we can think of this as a function of x. If for different x, we will get different sums. Some of those sums will converge, some of those sums won't. So here's the big question that we want to ask. For what x values does this series converge? That's the big problem we're going to mess with today. And there's some pretty straightforward ways to attack this. I'll give you a nice algorithm. And you're going to need to pull in your knowledge of other convergence tests at various times. But let's get some terminology here. So first off, x sub 0 is called the center of the series. And basically what we'll end up doing is we're going to figure out, actually, hey, let me ask you real quick. If x equals x sub 0, does this series converge? So if I replace x with x sub 0, what does that series turn into?
0.
Oh, yeah, almost, yeah, just this guy, right? So just that first term is left. If we replace x with x naught, all that other stuff dies. So we know that the series converges here. Converges at the center, and it always will. So let's actually write always here. Always converges at the center. In fact, the sum will just equal the first term. That's pretty chill. What we're going to figure out is how far away from this center can I move and still have convergence. So we're going to find this number r that tells us how far away we can move in either direction. This r will equal the radius of convergence. So r, let me write that up here. And then I'll show you how to compute it, but I just want to get the terminology out here. This is the radius of convergence. And what that is how far away from the center we can move x can be to have the series converge. So this point out here would be x naught plus r, and this would be x naught minus r out here. And some nice stuff is going to happen inside here. These boundary points are going to be potentially tricky from time to time. So we'll deal with those as we get to them. Let's just look at an example right off the bat. So let's say I had this series. So let's just do a bunch of examples now. There's a series. That's like that's so beautiful. It's like the simplest series you could possibly imagine, really. Just nice ones as the coefficients, this lovely polynomial that never ends and never goes forward anymore. So let me use this to show you the procedure for determining convergence. So first off, what's the center here? 1. If it was 1, it would look like this. So this series would have a center of 1. Notice how you see that quantity x minus the center all over. So this would have a center of x naught equals 1. What does x naught have to equal to look like that? 0. So here the center is 0. If you just see x by itself and you don't see x plus or minus something in parentheses, the center is 0. So let's just make a little note here. Center equals 0. Anytime it's just plain old powers of x, center is 0. So our plan. Step 1 is we're going to compute the radius of convergence. So the radius of convergence is going to equal, leave a little space here because I'm going to put brackets around that. Well, I'll just do it, and then we'll be ready. Limit as n goes to infinity of the ratio of the leading coefficients, the next over the later one over current one. It's got to be in this order, like this, and then we put -1 there. That means reciprocal. It's like 1 over this quantity here. Bless you. And let's just be really clear here, if this limit is not 0. If it is equal to 0, we'll talk about that in a minute. That's like great. If that happens, we're really happy, even though it looks really fucked up here. So we're going to compute this thing. This is the radius of convergence. Yes, blessings to whoever's sneezing.
Thank you.
So step one is to compute that. Let's do that for this problem. What are my coefficients? What is in front of the x? It's a 1. What's in front of the x squared? It's a 1. In front of the x cubed, it's 1. So this series just looks like this. Let's write it up. It's let's be really clear with some stuff. Let's put the -0 in. N equals 0 to infinity. But notice that the thing in front of the powers of x is just 1 the whole way through. So a sub n is just 1 for every n. You'll see in a bit that maybe there'd be like an n here, or like if the thing in front is changing, then we have to worry about that. But right here, constant coefficient of 1. So for us, an equals 1, an plus 1 equals 1, they're all 1. So r is, let's just write it all out, limit of absolute value of 1 over 1, all that to the -1, and would you believe me that that's all 1? We work it through? Yes, Abraham.
Why is an plus 1 still 1?
Because so a sub n, so a sub 0 is 1, a sub 2 is 1, a sub 3 is 1, a sub 0 is 1, a sub 1, all the a sub whatevers are 1. So no matter what this number is down here, the answer is 1. Does that help? Okay, cool. Other questions? I made life easy. So r is equal to 1. That's how far away from the center I can move and have convergence. Now, we actually have an old friend up here on the board that you may recognize if you think about it. But that's step one, find the radius of convergence. So compute r is really the first step. Step two is find the preliminary interval of convergence. And this is really just the interval. Let's draw a picture of it so you can see, because I think it helps. The center plus the radius, the center minus the radius on the left. So in other words, this interval, x naught minus r to x naught plus r. I'm leaving these ends open for now. This is the interval I'm trying to describe, right here. And I'm leaving the ends open because weird stuff can happen. We have to actually address those separately and think about what's happening. So for us, or for this problem, the IOC is equal to the center minus the radius up to the center plus the radius. So in other words, just negative 1 to 1. So let's actually write out, what does it mean that we just said that? So I want to summarize so that it's really clear. This means that if x is between -1 and 1, the series that we had converges for that x value absolutely, in fact. Because we already had these absolute values on here, so we're stripping away any plus minus stuff. Once you get this interval of convergence inside here, you get absolute convergence always. Absolute convergence inside that interval. The endpoints, no claims made. But inside there, any x value. So even if I pick x equals 0.99999, if I plug that into that series, I'm good to go. It still converges. But when I plug in x equals 1, well, hopefully you can kind of see the problem if x equals 1. Then we just got 1 plus 1 plus 1 plus 1 plus 1 plus 1, and that's forever. And that's just going to blow up to infinity. So we've got our preliminary. Step 3 is test each endpoint. And here I'm going to say unless r equals infinity, which we'll get to. Then you don't have to worry about it. You got them all. You got the whole real number line. So test the endpoints. So here our endpoints are -1. So x equals -1 and x equals +1. Let me stop, because I know I'm just rolling. I'm very excited about all this because I love it so freaking much. And I have a tendency to just keep going when I'm excited. So let me stop and make sure everybody's with me, or any questions. Bless you. And you're probably gonna need to work a few of these to like see this all through and then believe you can do it too. All right, so here I'm gonna test x equals -1. So I kind of mark that off here, and then I do the test. So plug, what does this mean? Plug x equals -1 in for x and evaluate the series. So here, it's going to look like this. Well, it started at 0, I guess. Right, so this is the series that we're evaluating. Does that series converge? Stop. Are you saying yes? Yes? Thinking? Are you saying yes? Yeah, you're okay. You're pulling back on that. Does this series converge?
Looks like it.
What does it converge to? And what test are we using? Do the terms die out? This can't add up because we just keep adding and subtracting 1. It's just going to oscillate forever. Think about the partial sums, right? How do we know if a series converges? We have to have the partial sums converge. And what's S1? It's just 1. What's S2? It's 0. What's S3 now? 1. Do you see how those are just going to bounce back and forth forever? Those partial sums do not settle down, so this series does not converge. Or just use the divergence test. Since the terms do not converge to 0 as n goes to infinity, this diverges. That we call that the nth term test or the divergence test. Let's say we didn't remember that. What kind of a series is this? What flavor? Alternating, right? So we go to that AST. We could do that too. We could just say, well, it's an alternating series, so I go to the AST. What are the various things I have here? Well, u sub n is just 1. This is the alternating part, and it's that times 1. That's always positive, so check, but that does not go to 0. So, no. So by the AST, this also diverges. So we do not have convergence here. Let's put a little note. You kind of want to keep a little picture going. Let's actually draw up our interval. I like to have a picture of this. You might like that too. It's one of the times we can draw pictures in our class. So let's see here. So here's 1, here's -1. We just tested this point. So no convergence there. I'm not going to include that point. I'm just going to leave it open so you can do those parentheses or just leave an open circle if you want. Maybe the open circle is a little clearer. Can you do me a favor and test 1, please? So here we have no convergence of any kind. What about out at 1? See if you get what is happening here. Oh, you're going to help, but thank you. All right, let's look at this together. What does the series look like at x equals 1? So now I'm going to test x equals 1. When I plug that in, the series looks like this. And the series is just this. It goes to infinity, right? The terms don't die out again. It's not alternating, but it just keeps piling up. So this diverges as well. So no convergence here either. And I'm done. Once you've analyzed these endpoints, we're done. So let's just see here, that's step 4. Done, just summarize. And we would just say the series converges absolutely in, and then we'll just give the interval -1 to 1. Let's say we're back like a week ago, and I gave you this series, and I asked you, what kind of a series is this? What would you tell me? Like way back, I think a couple weeks back, we're just looking at like the different flavors of series. We had like P-series, geometric series, telescoping. What kind of a series do we have there?
Geometric?
It's geometric, isn't it? This is just geometric. What's the common ratio? X, right? So this is geometric. This is like in retrospect, we're noticing this. Geometric with R equals X. What is the condition needed for that to converge? What do I have to have true about R? Less than 1. Yeah, but 1, absolutely. Has to be less than 1. That means that X has to be less than 1 in magnitude, and that's really just exactly what we just concluded a completely different way. So we came there to the whole thing in just a much more abstract way, but we knew that actually to begin with, that thing only converges when the common ratio is between -1 and 1. So we had a geometric series. Oh shit, what does it add up to? Oh my God, we have a formula, right? In the ratio of convergence, we have a formula. What is this actually equal to? What's the sum formula? First term over 1 minus the common ratio. I don't know what I'm right. I'm not going to look. Let's see if I can do it. Oh, that was fucking one. It sums up to that, right? That's the formula. So check out what is happening here. Something really interesting. We're starting to view these sums, these infinite sums, as functions of x. So this thing here actually acts exactly like this. And I want to show you something right now to give you some deeper insight into what is happening. Let's get this open here. I'm going to pull up some Desmos, show you something cool. Okay. There you go. Good job, buddy. All right. So let's look at 1 over 1 plus x. Just see what that looks like. That looks like that. It blows up when x is -1. We see that -1 can't be in the domain. And we get this nice hyperbola. So now let's look at the series we were using and saying it's the same. So here's 1. Here's just the first term. 1. Well, let's just do the first two together. There's 1 plus x. Oh wait, this was 1 minus x, wasn't it? Sorry. This was 1 minus x. There we go. It blows up. X equals 1. Okay. So notice how when I just take the first two terms of that series, it doesn't look at all like the function I'm claiming it represents, right? So we've got 1 over 1 minus x, and now, so versus, so I've got 1 plus x. This is actually the tangent line here, so this blue line is the polynomial that we're looking at. It looks like a tangent line right there. Look what happens when I start adding more terms in. And watch this beautiful thing that's about to happen. Now I went to the next term. Notice how they agree even more. When I just had 1 plus x, they only agreed at one point. Look at this, it's starting to mesh as we move further out. Let's keep going. So let's go to x cubed. And then let's go to x to the 4th. Do you see how it's kind of flipping, but the part of the functions that agrees is getting bigger and bigger, the areas where they actually completely agree? So, the center of this series was 0, right here. Here's 1 over here. And here's minus 1 right here. So I would expect that if I go out far enough, these series, this function, 1 over 1 minus x, and the 1 plus x squared plus x cubed, they're going to mesh perfectly, eventually, between minus 1 and 1. Let's move out a little bit further and just see that. What do I got, 5? Yeah, let's do a couple more. Look at that. Now let's zoom in. Let's see how good that actually is. Look at that. Those are indistinguishable. I don't even know how close. Let's move out a little bit further and see where they start to. Come apart. And the seam starts to break. I'm in way too far there. My God. Okay, look at that. Let's see, what is the x value where it starts to break? Boy, that's pretty good though. Let's see, let's come back down here. What is my x value right there? It's 0.348. So I can get the meshing to be better and better the further out I move. Let me point out another thing that I could say. That if I had this function here and you wanted to approximate it somewhere, you're like, what is 1 over 1 minus a third? Now, no one in their right mind would use an infinite series to answer this question. But we're not really in our right minds anyway. We're doing Calc 2. We're doing weird shit. But this is approximately 1 plus a third. And it's actually also approximately 1 plus a third plus a ninth. There's a better approximation. Here's a better approximation still. Wait, what's next? 27? Yeah. So the further out I get, the better, the truer this becomes as a representation of this thing over here. Let's do another one together. Let me give you one. Let's find the interval of convergence for this series. So that's n factorial in the bottom. Let's go through this one together. This is actually a really famous series. We're definitely going to look at the picture of it in just a minute. It's hinting at the big aha moment that happens in a class or two, probably on Friday. So first off, understand your series by writing it out. Don't just rely on looking at that. So when n equals 0, when n equals 1, 2, so forth, and etc. Does that make sense that that's actually the series? Yeah? So let's go through our procedure here. First off, I need to identify what are the coefficients. And what you should do is think to yourself, okay, wait, what is going on here? This is the A sub n right here. What is the center?
0.
0 is the center. Yep. When you just have powers of x, the center is 0. If the center is anything other than 0, you're going to see like x plus or minus something and powers of that. Then you'll know your center is not 0. So we have a center of 0. Cool. Let's do step 1. Let's find the radius of convergence. So that is lim. As n goes to infinity of a sub n plus 1. Let's write this all out over a sub n. I'm going to do the reciprocal. This formula is your friend for the rest of the semester. It's going to be very useful. So that is going to equal lim. N goes to infinity. Little tip on writing this: do it like we did with the ratio test, because sometimes those can get pretty hairy, right? And especially when you got those weird like pseudo factorial things that lots of people were having trouble with. You need to write that out like that. So could you just take a minute? Let me give you some time. Can you tell me what R is going to equal? I'll let you work on it for a second. And I'll start making some pretty stuff over here.
Is that first term a to the n plus n?
That is a to the n plus 1 right there. Is that what you're looking at?
Yeah.
Yeah, that's the, yes. So just taking the a sub n term and replacing n with n plus 1. Yes. Oh wait, got that ass backwards. So it's a sub n is this, right? What are we getting inside here when this simplifies? When we simplify the an over an plus 1 over an, what does it simplify to?
1 over n plus 1.
Yeah, just 1 over n plus 1, beautiful. So don't forget about how nice those factorials are in terms of canceling. And we just get this. But what is this limit?
0.
It's 0. What's 1 over 0? Be cheesy. What's 1 over 0? What do you wish it was?
0.
Oh, shit. Yeah, that would be pretty good. No, I was thinking more like that kind of thing. Yeah. 1 over a really small ass number is a really big ass number. But this piece here is equal to 0, so we'd end up with the 0 reciprocal, which is undefined. So remember when we were talking about this, I said This is the radius as long as this thing in here is not 0. If that thing in there is 0, the radius is infinity. So this, we're just gonna put equals infinity. So make a little note here. Note, if limit as n goes to infinity of a sub n plus 1 over a sub n equals 0, r is infinite. Let's put a little other side note in case, because we'll probably get there in the next example. Also, if this limit is infinity, what do you think the radius is? What's the flip side? If that equals infinity,
0.
yeah, then r is 0. Which would mean you can't move away from the center at all. You're stuck, you got 1 point of convergence, that's it. This says everything. This is everything is up for grabs. X can be anything and that thing will converge no matter what. We don't have to test endpoints. It's beautiful. So here, the interval of convergence, let's write this up. Since r equals infinity, the interval of convergence is all real numbers. There's not a number you can't put in there that thing won't converge absolutely for. Give you a second before I say the slightly heavier thing I'm about to say. Is there any questions on anything that I've been talking about? We feel good? Yeah, okay, I'm seeing some nods. I'm seeing some heads. Yeah, I'm seeing some like the little bobbleheads that sit on a dashboard kind of nods. So yeah, we'll do some more examples, but check it out. Here's the function we have. And look how I've got the sum represented in a nice sum way, and the slider represents the final thing we're coming to. So there's k equals 3. You can kind of watch this. Look at that cool behavior. As that thing flips back and forth. Let's pull out. Here's what we're seeing. Well, let's do it all the way so you can watch the wagon. It looks like it's like glued down, like somebody's tacking it down to the x-axis. As we get further and further out, that's like 100 terms right there. The last term is x to the 100th over 100 factorial. That's freaking huge. I think on Friday, you will see and believe that this is actually just this function, e to the x. That series represents that beautiful, one of our favorite calc functions, right? And let's prove it. Watch what happens here. See how it's meshing with that series? Let's get in here just a little bit. So there's like the worst approximation to e that ever existed, just saying it's 1. Here's the next best. Notice how when we have the first 2 terms, it's just the tangent line. And now you can think of that as the tangent parabola, the tangent cubic, and so forth. And then it's like super meshed up, and it's just that tail part that we're trying to model with polynomials, which is always very difficult. Notice how the tail always flies away because we are using a polynomial. But once you're out to infinity, there is no tail. That tail's gone. One last one. I'm not going to open any more WebWorks or anything. I don't think there's going to be any more WebWorks for credit this semester. I'll make some stuff, but it'll just be to practice and things like that. And also give you practice exam for sure. Things like that. Last one here. Can you do this whole one for me from start to finish? Please find the interval of convergence. next week is gonna be mostly working stuff together. See some nods of agreement? Yeah, cool. What's this inner limit? Infinity, so what's the radius of convergence?
0.
0, awesome. We cannot move away from the center. And what is the center? 0. 0 is the only point the series converges for. So R equals 0, and it only converges when x equals 0. And let's see that in the picture. You can see this happening, which is really cool. So over here, after you get that going, we did some little Desmos action as well. We can look at that series for various terms. Well, when k equals 0, it's just 1. Like your very first term, when n equals 0, you've got 0 factorial times x to the 0, that is 1. So that's what we're seeing there. And then when k is 1, I've got 1 plus x. Not so bad. When k is 2, I've got 1 plus x plus 2x squared. Then I'm adding on let's see, 6x cubed. And so check it out. Look at how it's blowing up around 0. And the further out we go, look at that thing. Let's get here. It's like, it's almost blowing up to infinity the minute you step away from 1. 1 is always cool. Let's look at that. It's almost got like asymptotes on either side. It doesn't, but it is rocketing up there because of that factorial. And like this is probably not straight in here. It's just the precision of Desmos is so not what this means. So this would be a curvy thing here, but you can see that we're just getting closer and closer to 0 before it blows up. Let's see. Let's just do. I just want to see if I can do 1,000. Same shit, right? But it's like a parabola that's getting time. Wait, can you guys not see what I'm seeing? Okay, no, nobody can see anything. Okay. Oh, it took a minute for it to die. It just died. Okay. That's what happens when your radius of convergence is 0. You just have convergence at the center because everything is just flying off to infinity, closer and closer and closer to the center. So my friends, one last thing I want to show you. So we got a little bit here. I want to show you some fun stuff. And it's something Scotty's been talking about. It's a classic. It's a classic result that is upsetting and wonderful and all sorts of things. So in the late 1800s, there was an Indian mathematician called Ramanujan. And he was self-taught, brilliant man, just unbelievable, like just got math books and was studying and taught himself about the infinite series, in fact. And was doing all this work that nobody else was doing because everybody else was telling themselves the things he was doing were impossible and shouldn't be done. So one of the things he did was the following. He started off with the series we started off with today. Started off with that power series for x, the geometric series, and said, okay, let's see, I've got a function of x on both sides. What if I differentiated this? So what if I took the derivative on the left and the derivative on the right, which is actually totally cool for power series. So what we're going to do is we're going to take the derivative. And if you did this thing on the left, you would get some chain rule action, double negatives, you get that. Probably believe that. That's not hard to believe. And on the right, I just got a polynomial. So 1 goes to 0, x goes to 1, x squared goes to 2x, 3x squared, right? So every single thing over here is just the power rule on down the way. So now we actually have, check it out, we actually have a new series. Here's a new infinite series, and here's what it adds up to. And then Ramanujan did something that was pretty extreme. He went outside the radius of convergence. Remember, our radius of convergence said this had to be between 1 and -1? So he's like, well, wait, what if x equals -1? Hold on. So I'm going to let x equal -1. And when x equals -1 over here, on the left, you get 1 over 2 squared. And on the right, what are you going to get? You're going to get 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus plus evermore. So he showed, in a way that people considered incorrect, that 1 minus 2 plus 3 minus 4 plus 5 minus 6 was a quarter. Well, that's pretty weird. So like we would say this diverges. That was the classic knowledge in the West. He was in correspondence with a very famous mathematician, Hardy, and he was writing him letters and they were writing back and forth. And he's like, check out what I did. What do you think about this? And Hardy's like, it's not what we consider correct, but it's really interesting and cool, and maybe there's something there. And then Ramanujan took this a step further. So the next thing he did was look at this sum. We need that fact to get to where we got. So the next series, and this is the one that I'll tell you what to Google. Google -1/12 after class. Find all sorts of stuff on YouTube. Then he looked at this series. The sum of all the natural numbers. Because it's kind of like, well, hell, if this adds up to something, you know, let's just go crazy. Let's see what this might add up to. And he called this C. Not like for the speed of light or anything like that, just C. And then he said, wait a minute, okay, so what's 4 times C? So 4 times C would look like 4 plus 8 plus 6 plus 6, oh wait, am I 4 plus 8 plus 12 plus 16, blah, blah, blah. And he wrote it in a different way. So 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12, right? And on down the way, let me write a couple more out so you can just definitely see the pattern. And why should it matter what I add to who? We're just adding numbers together. And then out here, plus 16. And he subtracted. He subtracted straight down. So we got negative 3C over here equals 1 minus 2 plus 3 minus 4 plus 5 minus 6. You see what he got? He got that. So he did this, and he's like, wait, whoa, that's a quarter. So negative 3C is equal to a quarter. Well, that means C must be negative 1/12. That the sum of all the natural numbers is negative 1/12. Which makes absolutely no sense at all, right? And this isn't something I want you to do in this class. We're gonna do things the like established way. People thought this was just childish, a lot of people did, but Hardy saw something deeper in this. Hardy saw there's something going on here that is profound. Turns out a little bit later, physicists would discover that this is actually true, and this represents some kind of crazy quantum phenomenon under the covers. That this negative 1/12 is a real thing, and that the stuff he was doing is real in the right reality. Like you can't take quantum reality and pretend it's anything about this reality. So if you ever see someone, I see this all the time, if you ever see someone invoking quantum mechanics who is not a quantum physicist, like an established quantum physicist, they are full of shit. Anyone who mentions quantum healing is full of shit, and they're just trying to take your money. I'm not saying the world isn't, I'm not saying you can't heal people, whatever. But the minute they mention quantum, run the fucking other way, because they don't know what they are talking about. One of the greatest physicists of all, Richard Feynman said, I don't understand quantum mechanics at all. So if someone tells you different, they are a hoaxer. I get in fights with people on Instagram and stuff like this about this all the time. I'll see like some healing thing and I'll say what I just basically said, and then people will come in, you just don't believe, and it's like, no, I'm just not gonna buy that bullshit. But anyway, there is a world where this does make sense. Did you have a question, Abraham? Or you just like?
What is the application for that?
It has to do with a function called the zeta function, and I'm just going to speak. I do not understand physics or quantum mechanics, let alone enough to even answer that question, except that I do know it has meaning in that world. And I'm trusting people who do know. Yeah, so it beats the hell out of me.
Fair enough.
Yeah. All right, that's it for today, friends. That's enough, right? You see that, you like pretty much shut down the rest of the video. So Friday, I believe we'll be meeting online. Keep an eye out. I'll keep you up to date on that. Of course, bonus points as always for showing up, participating. Thank you.
But like particularly not like I want to see him do like actual
Good one.
He doesn't know, like, picturing.
what?
I said, I feel like he's no theater.
Yeah,
Did you shut me down there, Gabe?
Oh, yeah.
Thank you, sir.
Looking at